So, hi all, welcome to the week 9 of problem solving session. Okay, so one key difference between the um, topics that we saw so far and the topics for today, maybe for the later half of the tutorial, is that so far we were only asking the question, what is computable by a machine? Okay, so whether when I say machine, it could be any model that you define. It could be a DFA, it could be a push down automaton, it could be a Turing machine, or some other model of your choice. But so far, whatever questions we asked, we never bothered about how much time it takes, how efficient, um, how efficient the algorithm is. All we are asking is whether it is even possible for the machine to compute something, some problem of our choice. So for example, for DFS, it had its limitations. It cannot compute all languages. That's something we saw. One example is a to the n, b to the n. This is something that a DFA um, cannot accept, cannot recognize. Similarly, PDA is slightly a stronger model, but it also has its own limitation. One example being this. Okay, and now we move to the most powerful model, which is the Turing machine. And yet, there are problems that are not even decidable. So there are, if you want to always halt, so if you want a total Turing machine or a decider, then for all L subset of sigma star, then the answer to that is also no. So there are languages that cannot be decided by a total Turing machine. Okay, so this is something that we know, but the main the common theme here was always that we were interested in what is computable. Okay, that's the only question we asked. We never asked how fast the computation is. And so um, we have this set of semi-decidable languages, co-semi-decidable languages. We had a decidable languages in this intersection, and now we are interested in problems that where we have a guarantee that okay, the Turing machine does halt. Okay, and now it makes sense to ask, okay, how much time does it take? It does halt, but does it take exponential time before halting, or does it take polynomial time before halting, and so on. Okay, here it does not make sense to ask about time. It doesn't make much sense to ask about time complexity, because we are not even sure that it will halt on every input. So therefore, within this world of decidable languages, we are now going to ask, okay, it always halts. Question is, how fast is the algorithm? Okay, and towards this we define what are called decision versions of the problem. So what is a decision problem? You are so these are the problems which give an input, which could be a graph, or let's say it's a graph, and I give you a cycle C, and the question is there does G contain C as a subgraph? Okay, and output would be yes or no. Or another example could be that input to you is a number in binary. So you have a number, and question is let me call this number n. Question is n prime? Okay, and you are going to say yes if n is prime, and you're going to say no otherwise. Okay, so yeah, so basically the answer is always going to be either yes or no. It cannot, it's a one bit answer, in other words. So output 1 if answer is yes, output no if the answer is no, but you cannot convey anything more than that. That's what the decision problems capture. Okay, whereas the input can be anything. It could be a matrix, it could be, yeah, we will see more examples of this later, but yeah. So now we are going to ask, okay, you have algorithm 1 and algorithm 2 for this. How do you compare which is better? Okay, so if there exists a Turing machine M, I mean total Turing machine M, which solves a decision problem P in deterministic so let's say this is a deterministic Turing machine, polynomial time. Okay, then you say that the language of M is in P. P is the complexity class. So within D, all the problems that have polynomial time solutions will fall into P. And notice that although I am defining the decision problem uh, right now, I mean the definition right now, you have definitely seen examples of this. For example, the halting problem which you had, HP, which is set of all m comma x such that m halts on x. This is a this is also a decision problem, because if m halts on x, then um, okay. Mm, okay, the decision version of this would be, I give you m comma x and output yes if m halts on x and no otherwise. So similarly, for every language that you can think of, you can always define a decision version of the problem like this. Okay. So I hope this is fine.
Yes, yes.
Okay. So okay, I'll come back to this maybe towards the end. This is something yeah, we couldn't finish in the previous tutorial. So we saw several um, ways of showing undecidability. One was the diagonalization, the other was um, reductions. But yeah, maybe we'll quickly define Rice's theorem and see these some of these problems, but maybe towards the end, after we are done with um, some P and P questions and so on. Okay, so yeah. Okay, so now that you know what is P, P is the um, set of all languages that have a polynomial time Turing machine. Okay, so we define a new class copy, which is um, the complement of languages in P. Okay, so question is it true that P is equal to copy?
Yes, yes, because I can always flip the outputs.
Hmm.
So by flipping the outputs, say I would be having the answer of yes and no both for the complement of the problem. So P is equal to code.
Exactly. So you have that L bar is in P, therefore there exists a deterministic Turing machine M, which is runs in poly time, and L of M is equal to L complement. Okay, so now we can come up with a machine M prime, which is as follows. Uh, Run M on Z if M accepts, then we are going to reject, and if M rejects, then we are going to accept. So what is the language of M prime? The language of M prime is exactly the complement of, which is nothing but L bar complement, which is nothing but L. So therefore there exists a polytime DTM M prime such that language of M prime is equal to L, and therefore L is also in P. So therefore copy is equal to P. Okay, so what we did is, you started with the assumption that you started with the fact that L bar is in P. That's something we know. So by definition there is a polynomial time Turing machine for accepting language L bar, and let's say M is that
Ma'am,
machine.
what is PCOP?
So
Copolynomial.
it's a complement of polynomial, the class P.
Okay, okay.
Okay. Okay, so yeah, so we constructed a machine M prime which runs M on its input and flips the acceptance condition. If M accepts, then it rejects. If M rejects, then it accepts. So what is the language of this machine? The language of this machine is everything that is not in the language of M. So it's the complement of L of M, which is nothing but L. Okay, so therefore you have a deterministic deterministic polynomial time machine for L. This is true for every L bar which is in P. Therefore copy is equal to.
Deterministic polynomial time machine means what?
So we are always so for from now on we will always be talking about Turing machine. So whenever I say machine, we will mean a Turing machine. Okay, deterministic meaning your Turing machine is deterministic, given a state, given a yeah, given a symbol on the tape, there is exactly one transition that it can perform. This is the sorry, this is the delta function that we had, right? The delta for this Turing machine, the transition function is deterministic. And yeah, did I say polynomial time also? Then in that case what we mean is this Turing machine runs for polynomial time. So if your input size is n, then the number of steps for which this Turing machine will run is a polynomial function of n. That means it can be when we say polynomial time, it means if input size is n, then the machine runs for at most n to the c steps for some c. Okay, so this c could be 2, it could be 2000, or it could be much larger, but it is guaranteed to be a constant. So some power of n, it will run for that many steps at most. It won't run for more than that. For example, I'm not allowing it to run for 2 to the n many steps. This is not allowed. Okay,
Exponential not allowed.
yeah, anything more than polynomial is not allowed.
Okay, okay.
Okay, then we will say that that language is in P, because there is a machine accepting that language which runs in polynomial time, and the machine is deterministic. Okay. Okay, so yeah, so is this proof clear? Why this class
Ma'am,
scope?
within a rectangle box, you have just you are doing some proof. So can you explain it, illustrate it?
Yeah, so uh, yeah, so I want to show that the language L is in copy, right? So that means I want to show you a machine which runs in polynomial time. Sorry, I want to show that L is in P, so I want to show you a machine for L which runs in polynomial time. Correct. So what I'm doing is I'm giving you an explicit construction of that machine. Here is one machine. What it does is, given its input, it's going to run the machine M on the same input. Okay, so um, M will either accept or reject, that we are sure, because it is a decider. Okay, so after some polynomial number of steps, so this will run for polynomial many steps, because L of M is in P. Okay, so after those polynomial many steps, it will either accept or reject. So if machine M accepts Z, then what M prime does is, then M prime will reject Z, and if this machine M rejected Z, then M prime will accept Z. So it is doing exactly the opposite behavior of M. Okay,
When it will accept, which condition or situation create for accept
for
the by a
acceptance of
machine or reject by a machine?
no, I don't understand. Are you asking whether when M will accept, or are you asking when M prime?
M accepted, what conditions will occur to accept the M and reject M condition, when what situation and condition?
Yeah, that totally depends on the language. So I mean, so if you have a language which is, let's say, 0 to the n, that's all. Okay, then when will the machine accept? It will only accept when the input given to it is 0 to the n. So I mean, the whether M is going to accept or not depends on what the language is, right?
Yes, sir, yes, right.
Okay, so yeah, yeah. So because M prime flips whatever M was doing, its language is complement of M's language. Therefore, you have a polynomial time Turing machine for the language of M prime. Okay, so that's what this part is the yeah, is the correctness and time complexities. Okay,
Is the correctness of time complexity means what?
yeah. So correctness meaning, whenever you write a machine whenever you give a description of a machine, correctness would mean that the language accepted by the machine is same as the language that you want. Okay, so in this case, what is the language that we wanted? We wanted this L, we want to show it is in P. Okay, so yeah, so that is what we ended up showing, that L of M prime is actually equal to L. So this is the correctness part. And complexity means what is the time taken by this machine. So time complexity. So what is the time taken by this machine? First, it runs M on Z. This will take polynomial many steps, because by definition M is a deterministic polynomial time machine. Then after running M on Z, and after getting to know whether M accepts or rejects, it's just going to flip. So this is just a constant time operation. This is just an order 1 operation, or constant time operation. So what is the total time? Total time is this time plus this time, which is nothing but polynomial. Okay, therefore we know that L is in P, because there is a machine which runs in polytime for it. So this part is the complexity analysis, and this part is the correctness.
Okay, fine, man.
Okay, so okay, so yeah, so you can ask the following question instead of a deterministic Turing machine. Okay, so let me. Okay. So P is the set of all languages such that there exists a deterministic Turing machine M which runs in polytime and L of M is equal to L. Okay, so now you can ask what happens if I replace this de- deterministic machine with a non-deterministic Turing machine. Okay, what do we mean by non-deterministic Turing machine? The transition function delta is allowed to have multiple transitions. Okay, so instead of on a q cross could be 2 to the q cross okay, so it could make so in deterministic case you only had one single choice, it goes to on reading something, it only takes one specific action. In case of non-deterministic Turing machines you are allowed to make several, you have several different choices that you can take. That's what this represents at the, yeah, you need not have only one set of transition. Okay, so what happens if I replace this Turing machine with a non-deterministic Turing machine? Then the class of languages that can be accepted by non-deterministic Turing machines that run in polytime such that L of n is equal to L is what we call the class NP. Okay. So by definition, what can you say about P and NP, which could be a potentially larger class? So is P a subset of NP or is NP a subset of P?
P is a subset of it.
Right, because every every deterministic Turing machine is also a non-deterministic Turing machine where you don't make multiple choices, right? I mean, because this just says that you can make choices. So if you don't make multiple choices, then you are still a non-deterministic Turing machine. So by definition, something here is also here. So to answer this, if L is in P, then L is also in NP because a DTM M is also by definition an NTM. Okay, therefore P is a subset of NP. The question is whether the other way round is true. Okay, so that is something we don't know, and maybe in the later part of the course we will explore, um, possibly explore. I'm not sure. Okay, so however, this is something that we know. Okay. Okay, so let's. So you're given three statements, and you want to choose which of those are correct.
So statement one is that it is known that every language in P belongs to NP. Is that right? And it is known that every language in NP, no, this is not correct. It is known that statement three is it is known that every language in NP can be decided in exponential time. So it is known that every language can we decide this in the exponential time by using the DTM? Yes, that would require exponential amount of the time. So that is true. So one and three, C. C is the right answer.
Okay, yeah. So sure. So maybe we will see more on this if there's exponential, the class exp and so on, that is covered, then maybe we'll talk more about it later. But yeah, but the question is, if I change this polynomial time to exponential time, then if I, let's say, allow more time and keep the rest of the definition same, then you get a class which is called exp, which is the set of all languages that can be accepted by a deterministic Turing machine in exponential time. And you can similarly define a non-deterministic variant of exp, where you allow the machine to be non-deterministic but give it allow it exponential time. Then you get a class which is called nexp. Okay, and so on. You can, I mean, yeah, you can come up with your own time constraints and define classes based on that. And there are several classes that are already defined based on, yeah.
So what's the relation in between the EXP and NP?
Yeah, we know that NP is contained in exp.
So does this mean that there are problems which requires exponential amount of the time using the DTM, which are not solvable in the polynomial time using NTM?
And you're asking that whether there is a language in exp, but exp is not, but L is not in NP.
Yes, yes.
No, we don't know whether there are such languages. Yeah. Um,
Is this an open problem?
yeah, yeah.
Okay, all right.
So I'll just remove this so that there's no confusion. Okay. Okay. So also the answer to that would give you an answer to P versus NP, because P is definitely not equal to, P is strictly a subset of exp, but we have P is contained in NP, which is a strict subset of exp. Sorry. And P is a strict subset of exp. So if it were true that um, NP is equal to exp, then that would mean that P is not equal to NP.
Oh, I see. If NP is equal to EXP, then oh, so how will this deny that P is not equals to NP if NP
Yeah,
is equal to EXP?
because we know that P is a strict subset of exp. So this would imply that P is a strict subset of NP. This means that P cannot be same as NP.
Yes, right. Thanks. Thanks.
Okay. Okay. So I'll just copy this definition. Okay. So this is how we define the class NP, the set of all languages that have a non-deterministic Turing machine which runs in polynomial time. Okay. There is an alternate way of seeing this, an alternate definition of the class NP. Okay. And um, yeah. So you say that a language L is in NP if there exists a deterministic Turing machine M which runs in polynomial time such that um, yeah, for all x in the language, if there exists a small certificate. Okay, by small we mean it's polynomial size, it's polynomial sized in terms of the length of x. So if the length of x is n, then the length of y can be at most some polynomial, uh, in terms of n. Okay, such that what this m does is, given x and y, it can verify whether m of xy is equal to 1. So such that if and only if, okay, so I'll write it here, such that m of x comma y is equal to 1 if and only if x is in the language. Okay, okay, so in
Uh,
other,
and this M is a verifier.
exactly, this m, yeah, this m is a verifier. That means if x is in the language, then there is a verifier m, which is a polynomial time deterministic machine, such that you can come up with a small, so this is also called a small witness or a small certificate. M is called, yeah, maybe I'll erase this and write here. So this m is also called a verifier, an efficient verifier, because it runs in polynomial amount of time. And this y is called a witness or a certificate. In fact, it's a small certificate because the length of the certificate is bounded by polynomial size, and this verifier is efficient because it runs in polynomial time. Okay, so if x is in the language, you can come up with a small certificate such that you can efficiently verify that x is in the language. If x is not in the language, then it does not matter whether you can come up.
Y belongs to 0, 1 whole to the power x, mod x. How can we represent the language?
The language of y is just a string, it's not a
Yes, yes.
language.
Which kind of string it is? Can you give an example?
It is, okay, so I think this length of x is confusing, so let me write it here. So let's say length of x is n, then it's 0 1 to the n, y is in 0 1 to the n, so it is, sorry, n to the c. So it could be some string of, let's say n is 5 for you and c is 2, then yeah, then y is in 0 1 to the 5 to the 2, so it could be some string of length at most 25. For example, it could just be 0 1 0 1 0.
Is it the same number of 0 and same number of 1? Nor
No, it is
or
any string. It is any string of length at most 25.
okay, okay, okay.
Okay, so this is same as 0 1 to the 25. So although I am writing 25, this is really at most here. So this is at most 25. So this is the set of strings of length at most 25. Okay, any string of length at most 25. Okay, so maybe this definition will get clearer with more examples that we will see. Okay, so um, yeah, so let's say that let us do first part. So let me just take some other example, st path. So here is the problem st path, which is defined as follows. The input to us is a graph G, and the output is yes if, yeah, and vertices s and t, yes if there is s to t path in G, and no otherwise. So for example, let's say we have a graph, let's say it's not undirected, 1 2 3 4 5. Okay, suppose this is the graph G. Okay, so I'm giving you this graph G as input, and S is, let's say, 1, and T is, let's say, 4. Okay, so what should be the output of this problem? It will say yes if there is a path from 1 to 4 in the graph G. So in this case, if you go from 1 to 2, 2 to 3, and 3 to 4, then you have a path from 1 to 4. Okay, so in this case, the algorithm should say yes, there is a path. Okay, and for example, let's say you give the same graph, but S is 1, and okay, maybe S is 2, and T is 4. Then what should be the output of this problem? Is there a path? Yeah,
2 to 3, 3 to 4.
that's right. Okay, so okay, maybe I should have taken, let's say, 5 to 5 and 4. Sorry. Oh, even then you have a path. So do you see? mm, okay, I guess I've created an example where you don't have. Yeah, this is a completely connected graph, right? Okay, but if I add a new vertex 6, and now if I say S is 2 and T is 6, then the answer should be no, because there is no path from 2 to 6.
Moreover, while defining this NP, only only one case was mentioned when the string is the part of the language. For all x which are the part of the language. So what about those strings which are not the part of the language? For which, how to define this verifier and the certificate?
Yeah, so if X is, yeah, we have this if and only if condition here, right? So if X is not in the language, then no matter what Y you take, the verifier will always say no. Okay.
Yes, yes. Can you show that if and only if condition again? And how does this include this second fact that if X is not the element of the language L, if P bidirectional Q, then
Okay, so yeah, let me remove this blue thing. Um, yeah, length of X. So X is in the language L if and only if there exists a Y of length polynomial sized such that, let me bring this here, such that m of xy is equal to 1. So the other direction, so if X is in L, then there is a Y such that m of xy is 1, but other direction would be if X is not in L, then there exist becomes for all. So no matter what Y you take, so in other words, the contraposition of this or this direction is that if X is not in L, then no matter what Y you take, the negation of this would be that m of xy rejects, or m of xy is equal to 0.
yes, yes.
Okay, so yeah, so so the question is, what is a good certificate for this, or what is a verifier and what is a certificate? So what is the certificate? A certificate here could be that you, if the answer is yes, then how will I convince you that the answer is yes? I'll just give you the path. So certificate would be a path from 1 to 4. So in this case, the path is 1 to 2, 2 to 3, 3 to 4. Okay, so what is the verifier algorithm? The verifier algorithm will look at each edge. It will check if 1 to 2, it will check if there is an edge. Is 1 to 2 an edge in the graph? Indeed, 1 to 2 is an edge. Then you look at the next thing, is 2 to 3 an edge in the graph? Yes, 2 to 3 is also an edge. And then you ask whether 3 to 4 is an edge, and you can check whether there is an edge 3 to 4. Okay, and now the verifier is convinced that yes, the certificate is correct, and indeed there is a path from 1 to 4. Okay, so what is the certificate? The certificate is S2T path. And what does the verifier do? Verifier checks for um, existence of each edge in the path. Okay, so what is the length of this certificate? We wanted the length of the certificate to be small. So let's say the graph has n vertices. Then in terms of n, what is the size of this certificate? What is the maximum size of this certificate?
So maximum size of the certificate would be the longest path starting from, and then if we have got n number of the vertices, then the length of the path would be of the order of n. I mean maybe n minus one.
Exactly. So, um, yeah. So, what is the length of this certificate? The length is at most the, or this length is exactly the size of, or length of, yeah, I should call it size of certificate. This is nothing but length of S2T path. And what is the length of S2T path? It can be at most the longest path in G, and the longest path can be of length at most n minus 1, where n minus, if you're looking at edges, then it's n minus 1. So this is nothing but order n, which is something we allow, right? So we are allowing um, polynomial size certificates. And the other question is, how fast is the verifier? What is the time, um, yeah, the time complexity of the verifier? Okay, so how much time does this algorithm take? What is the algorithm? Algorithm looks, given a path, it checks whether 1 to 2 is an edge, 2 to 3 is an edge, 3 to 4 is an edge, and so on. So there are n minus 1 edges to check. Okay.
Yes.
And each check is just an order 1 query. So there are n minus 1 adjacencies to be verified, and each check is order 1. So overall this is order, still order n, just polynomial time algorithm. So therefore this language is in NP. Okay, so now let's take this example. You are given, okay, maybe let's take something simpler first. Okay, let's say you are given which is the, yeah, let's say this is D, and the input to you is a Sudoku problem, which is you're given a grid, and yeah, each of them have numbers to be written, and each of them must appear exactly once. In every row, in every column, all the numbers should appear exactly once, and within each small grids, each number should appear exactly once. Okay, so I mean your standard Sudoku problem, and you should say yes if it is a valid, if there is a valid solution, and no otherwise. Okay, so some numbers are already written, some numbers are to be filled, and you want to check whether there is a valid completion. Okay, so is this problem in NP?
Yes, yes, because if you tell me the solution, I would be able to verify the solution in the polynomial time. So certainly, then
Yeah, so what is the certificate?
the certificate would be, I do not know this Sudoku puzzle, but the certificate probably would be the I mean, I don't know row, one row elements or one column elements or one diagonal elements, right? And all are there. Their sum is equal or what? What is
Each let's say the size of the Sudoku is 9 cross 9. Okay, this is a 9 by 9 matrix. Then in every row, all the numbers from 1 to 9 must appear exactly once. So you can't have two occurrences of the same number and no number can be missed. So in every column here, in every row here, all the numbers 1 to 9 must appear exactly once. Within each grid also, within each small grid of size 9, all the numbers from 1 to 9 must appear exactly once.
Oh, so in that case, I need to check n square number of the entries. I
N
mean,
square, why n square? The input to
because
you, the input to you is this 9 cross 9 matrix.
input is 9 cross 9, but then some of the entries must have been left blank. And so even if this is 9 cross 9 matrix, then I would be requiring all the values, isn't it?
Yeah, so you can, that is still a small certificate, right? Because so what is the size of the certificate? If certificate is, you give me the total, like fill the entire matrix with
Yes.
values. Okay, so what is the size of this matrix? It's still 9 cross 9, it's still polynomial.
Yes. Yes. 81. So that is what I told, that n square number of the entries are required. So by considering that the size that the Sudoku is n cross n.
Oh, okay, yeah, okay, but if, yeah, 9 cross 9, if I call this to be n, then okay, sure.
So then for the 9 square, for a certificate of the size say n square, how much time is required to check that whether there is no repeated element in a row or in a column or anywhere else? So for this repetition, I need to check say n number of the entries in a row. And so once I check for the rows, would it automatically confirm the columns, or do I need to check for the columns explicitly? I need to check for the columns explicitly, I guess. If that is the case, then I'll have to make further n square. I need to make effort of the order of n square to verify. And diagonal is not the constraint here in Sudoku, I guess. Yeah. So then I would be requiring n square amount of the effort to verify that whether this indeed is a valid solution.
Yeah, so there are yeah, so let's say that the size of this matrix is n cross n, then there are n rows, there are n columns. For every row we are going to check whether each number has appeared exactly once. So um, this will take order and time, and this, each of this will take order and time. So totally this is order n square, this is also order n square, because it's order n for each column, order n for each row. Additionally, we have these small grids. There are n small grids. For each grid we are going to check the same. So there are n small grids, and for each of them again we are going to check whether each element appears exactly once, and this will also take order n square time. So if you sum all this up, we are still running in order n square, which is polynomial time. So this is polynomial time. Okay, so yeah, so far the coming up with certificates and verifiers for these algorithms was very simple. For example, in the case of st path, the certificate was that you just show me the path, and verification was that I'll check whether that path was indeed a valid one, whether it actually exists in the graph. Similarly, for Sudoku here, you, what is the certificate? The certificate is that you give me a completely filled n cross n matrix where all the entries are filled with some number or the other. And what does the verifier do? The verifier checks whether the three constraints that a Sudoku puzzle must have, that each row has all distinct numbers, each column has all distinct numbers, and each grid has, small grids have all distinct numbers. All those three conditions can each be checked in polynomial amount of time. So totally we are still running in polynomial time. So both the conditions are satisfied. Therefore, this is also in NP. So okay, um, maybe
Can you repeat please? How can we consider that Sudoku problem is NP?
okay. So is the certificate clear? What is the certificate? The
Can you repeat please?
Yeah. So
Sorry.
in the input that's given to you, some of the entries are filled, some entries are missing. Okay, and you want to check whether it can be filled in such a way that all the three constraints are satisfied. So what is the certificate? The certificate is that you're going to give me a matrix, a n cross n matrix, where all the entries are filled with some number. Okay, some number between 1 to n. So it's a totally filled matrix. The input was partially filled matrix, whereas what the certificate is going to be some some completion of this. Okay, where every element is every cell has some number.
Means each row and column and 3 cross 3 box must contain all digit without repetition.
No, the certificate does not care about whether the constraints are met or not. The certificate is um, just a matrix which has numbers written on it. It may or may not be correct. Okay.
May or may not be correct means what is you can addressing may or may not be correct.
Meaning the certificate by itself does not need to ensure that all the constraints are all the conditions are met or not. That is something that the verifier will take care of.
Okay,
Okay, so
continue.
yeah, so the verifier is going to uh, take the certificate and it's going to make all the three checks whether all the three conditions are met or not, and that it can do in polynomial time. Okay, this
In grid equal to arrow equal to in big O of n time means why it is a big O of n? Can you explain?
so if I give you a row which is of length n, okay, I give you a row of length n, and there are some numbers that are written into this. Okay, some numbers from 1 to n, they may or may not be repeated. Okay, so some numbers are written and you want to check. Okay, so you are given a row of length n, you are given an array of length n which contains numbers from 1 to n. Okay, may repeat, may not repeat. You want to check whether it contains all the elements of 1 to n. So how will you do it?
One by one linearly
Exactly, so how much time does it take?
n
Yeah, so
big
that's
O of n.
why we wrote order n. Similarly, same thing will happen for the second case and the third case also. You are given a column, you want to check whether all the it contains all distinct elements from 1 to n. Each of those will take order n time. Okay.
Okay, but internet connection is very poor in this your location. So you are preach.
I see. Is it the case for everyone?
For me, it's okay. I can see you. Your video is fine. Audio is also fine.
I see. Okay, okay. Sure. Um, okay, so maybe we'll do a couple of more examples from this. So, mm, okay. So maybe let's take the first question. Okay, so the question is, you're given a number n. Okay, this is given in binary, by the way. Okay, you want to check. I mean, we already know there are ways of expressing every decimal number into binary, right? So, I mean, you can, for example, one standard way of doing this would be if n is equal to 5, then how do you write it in binary? You write it as 101 and so on. So, it's a binary representation of n. Okay, so you want to check if n is composite. So, output yes if n is composite, and you will say no otherwise. Okay, so question is whether this problem is in NP. So I'll call this problem as composites. Okay, so question is whether, yeah.
So I do not know what is the relevance of representing n into the binary, but if n is in decimal, then the certificate could be that give me a number and which is not 1, which is not n, anything different from 1 and n. And if that number divides this number n, then n is the composite one.
Hmm.
But what is the relevance of representing this n into the binary here?
Okay, yeah, I'll come to that. So what is the certificate? The certificate would be that you give me a number m, which is, yeah, n, which is a natural number, and what does the verifier do? The verifier checks if m divides n.
But then this m should not be a 1 and this m should not be an n.
Yeah, yeah, and m is not, sorry, yeah, okay, and
No.
if yes, then if it does divide, then you say yes, n is composite, otherwise you say no.
If you forget to negate this, m is not an element of a group.
Sorry, oh right, yeah, m is not 1 and m is not n. Okay, so okay, so let's say that okay, so one reason why I say this is binary is because um, I mean, when we define problems, we are always going to look at a 0 1 alphabet. Okay, so because everything can be encoded in 0 1, so the alphabet for us is always 0 1. Okay, but what happens when you write n in binary is that if number in decimal is n, okay, then when you write it in binary, what is the length of that number? So let's say x is binary representation,
Log of n.
yeah, of n, then length of x is log of n. Okay, so I'm not really given, I'm given this x as input, which is the binary representation of n. So the length of input for me is now logarithmic, it's not n, it's logarithmic in n. Okay, so that means how much time am I allowed, how much time can my verifier run for? My verifier can only run for the length of input to some constant, some polynomial time in terms of the length of input. So what is length of x for us? Length of x is log n. So my verifier is only allowed order log n um, to the c amount of time. Okay, so this is why the opposite of this question, which is checking whether a number is prime or not, becomes difficult. Okay, so if I change this problem to, I ask for primes, okay, and instead of composite, let's say I want to say yes if number is prime and no if number is not prime, then giving a certificate becomes difficult. Okay,
Why so?
because if a number is not prime, if a number is prime, that means no number smaller than it divides that number. So how will you give me the certificate?
So that has nothing to do with the length of whether the n
Yeah,
is represented in
so
binary.
let's say I don't represent this number as log n. Okay, I allow you n amount of space. uh, let's say the input size is n. Okay, then
Yes,
you can give me a certificate, right? What will be the certificate? The certificate would be all the numbers up to n, less than n.
yes,
And what I'll do is, for each of these numbers I'm going to check whether 2 divides n, 3 divides n, and so on. And the length of this certificate is still order n, and the running time of the verifier is still order n.
yes.
Yeah, so yeah, one thing is we always deal with 0 1 alphabet, therefore we always write it in binary, and that, as a consequence of that, it will shrink the size of the input. So therefore, yeah, we need to be careful about the length of x in that sense. But yeah, let me just remove all of this if it adds to confusion. Okay. Okay.
So what is the general nature of, I mean, even though this is primes in P is in P, I mean, it's polytime, it's okay. But otherwise, this primes, whether primes is in P, I mean, whether the given number is a prime or not. So this can be the element of NP. Where is the issue with this? Could be the element of NP.
Yeah, it is. Yeah, it is an element of NP. The only thing is that I cannot. I mean, I can. The certificate needs to be designed a little more like cleverly. This certificate of giving all the numbers between 1 and n, that won't work. But you have to come up with a better certificate, a shorter certificate.
Ma'am, binary, it is input is n equal arrow binary, and output yes. What is when it will be yes, or when if n is composite? Composite means here what represented? How can we give me some ma'am examples?
Yeah, sure. So, um, yeah. So example one would be, let's say n is let's say 7. So input to me would be a binary representation of 7, which is 4 plus 2 plus 1. Yeah. Okay. And output should be, you should say, so is 7 a composite number? Is there any number other than, does there exist a number m is not equal to 1 and m is not equal to 7, such that m divides 7? In other words, in other words, we are asking whether this is not a prime. So 7 is a prime number, so output should be no, right? Okay. Other example would be for let's say n is 10, and so in binary the number is given to me as 8 plus, yeah, so output should be yes in this case. Sorry, I think yeah. Okay, we are good. So if n is composite, you want to say yes. If n is not composite, you want to say no. Okay.
So how this verifier is going to run an effort of the order of log n here, uh, the log n raised to the power something. How
Yeah.
is that happening?
Yeah. So yeah. So you are given two numbers, two binary numbers. So let's take this example. Okay, let's take the yes case because we care about the verification only in the case of yes. So let's say number that's given to me is input is 1010. So length of x is 4. I mean, it doesn't really matter what the numbers are, but okay. What is a certificate for this? A certificate would be a number that divides n. So 2 divides n. Okay, so certificate is 2, but the binary representation of 2 is 10. Okay, so what does the verifier do? The verifier wants to check whether 10 divides 1010. So how would you do that? You would keep on subtracting. Okay, so this is a log n bit number. Input was log n bit. This is another number which is at most log n bit because it's a number smaller than the input, so it cannot take more bits. You have two log n at most log n bit numbers. You want to check whether the smaller number divides this. What you will do is one thing would be you just keep on repeatedly subtracting. So you subtract this in place. Okay, so this becomes 1000. Then you subtract again and you get 110. Okay, from 110 you subtract a 10 again, you get 100. You subtract a 10 again, you get 10, and you subtract a 10 again, you get a 00, and that means this number 10 completely divides 1010.
And after how many number of the steps we would be able to confirm this?
Okay, every time you are dividing the number by at least half.
Yes. Right.
So so in log n number of steps you will be done.
Yes. And what if we do not? What if we consider this into decimal only? Then how will this pose a problem for the prime number?
Yeah, the problem is not in the fact that the division is not in the complexity of the division algorithm, but rather in the fact that you don't have a small certificate in the first. I mean the certificate which we had 2 3 comma n minus 1, that certificate itself was large.
It's okay. The certificate could be of the length n. That is fine. We had the certificate of the size n square in the case of the Sudoku. So
No,
here
no,
is the
no. So
problem.
that n square is no. The input size is n square. Okay. What um, what is the size of this input totally?
N square.
N square. Yeah,
And the size of the certificate was also
was also n square.
n square. So then I think having a certificate of the size n is not the problem. I mean, for the primes problem.
But we don't have a. I mean, there is a huge difference between. So how much space are you? How much size are you allowed? You are allowed length of x to the c.
Polynomial in terms of polynomial. The size of the certificate could be a polynomial in terms of the length of the input.
Yeah,
Yeah,
polynomial in terms of length of x. So what
yeah.
is length of x? This is log n to the c.
So represent n as a normal thing. I mean, not in the binary. Say the n is represented in unary. Then, if it is
Okay.
if it is unary, then I can have the certificate of the order of n, and then I would be able to check whether this number is a prime number or not. By considering all the divisors, say 2 to n minus 1.
Yeah, then you can surely run the same algorithm. Check for each number whether it divides n or not. you'll still be polynomial in terms of n. That is correct, yeah.
Yes, yes, correct.
Okay. Are there any questions about anything that we discussed so far?
So what would that example be wherein the verification itself requires exponential time?
Hmm. Okay. So, one classic example of this would be, for example, chess. Okay. So, yeah, requires is a strong word, but what I mean to say is, showing that it is in NP is not easy. Okay. One example would be, let's say you have this standard chessboard. Okay. And yeah, I'll not draw all of it, but it's an 8x8 board, and these are white and black cells. Okay. Okay, all of it. Okay, so now you are in the middle of a game. Okay, two players are playing a game, and you just entered at an arbitrary point, and the configuration is changed. Now maybe the king is here, the the rook is here, I mean the queen is here, and so on. Okay, so the some pieces are killed and so on. You are in the middle of the game, and the question is whether there is a chance at all for white to win. Okay, so this is white and this is black, and so input that's given to you is this chessboard. Okay, you know that the positions of all the pieces. So you know that the king is here, the queen is here, and so on. That's the input, which can be represented. Yeah, you don't need much space to encode that. And output is yes if white white has a winning strategy. What do I mean by winning strategy? Oh yeah, and by the way, you also know which player's turn it is. Okay, let's assume that it's white's turn. Okay, so that's something you know. Okay, so what is a winning strategy? That means, is there a sequence of, is there something that the white can play, some move? Okay, if there is some move that white can make, such that no matter what the black plays after that, so no matter what black plays after this, there is still something else that the white can play. Okay, and this sequence keeps on happening, so there is some choice that white can make, so that no matter what black plays, there's still something white can play over and over again, so that finally white wins. Okay, in the end. Whereas I don't know if some of you are familiar with the game, you can, I mean, you would know that there are configurations where it's not possible to win no matter what you play. After some point, you're gonna lose the game. That's not just true for chess, that's true for a lot of simple games as well, right? You encounter a situation where no matter what you play, you are just gonna lose. Okay, so the question is whether there's a winning strategy. Okay, so the what is a certificate for this? A certificate, a simple certificate, what would be, you tell me what should white play, so that no matter what black plays, what should white play next, and so on. But what is the size of this?
So size of this, I mean, would be huge, but
Yeah, so there is some move that white makes, after which the black can make several many moves. For each of them there is some move that white makes, such that black can make so many moves. Sorry. Okay, so many moves, and this graph is just expanding, right? This is exponentially. Even if you play this game for n steps, okay, This is the first step where white plays, the second step black plays, third step white plays, and so on. What will be the size of this um, what will be the size of this tree?
Yeah, so this would be exponential, and I guess that even this problem is not even there in the P space. I mean, we use this like Antakshari problem, and wherein, yeah,
Yeah, because we don't know how many steps you're gonna need to convince.
yes.
Yeah.
But then
So,
my query was slightly different. My query was that uh, in this scenario, the verifier itself is going to take exponential time. So I have got a certificate, and the length of the certificate is small, is polynomial, and then but then the verifier is going to take exponential time. So I thought of the negation of the satisfiability. Probably I don't know to what extent will that be true. So I thought of that for the negation of the satisfiability, for the yes instance, probably the verifier is going to take exponential time. I'm not sure, but I thought of it.
yeah, so we don't know an answer to that because, again, that would imply separation of NP and co-NP.
Oh, I see. Okay, okay. So, I mean, so this seems that as if, but then this seems that everything is NP. But then we know that there are problems beyond NP as well. So therefore, there must be some problems for which even if you give me the certificate, it will be very, very difficult for me. Has to be very, very difficult for me to verify that whether this indeed is a
Yeah.
solution or not. So
Yeah,
what
so
are those
yeah,
problems?
so that would be some problem in any XP because that problem, yeah,
Oh,
yeah, huh. Because this will come directly from the time hierarchy. You know that NP would be separate from any XP. So
ye-
definitely there are languages in any XP which are,
oh, I see. Okay, yeah, yeah. Thanks. All right.
yeah. Okay. So yeah, is everything clear so far for others also?
Now, no doubt, ma'am, Hamilton path, given a graph G and check if there is a Hamilton path in G. Can you explain it?
Yeah. So okay. So we did this one right now, right? This is something we did. That's all. Sorry. So you are given a graph G. Okay. Okay. Suppose you are given this graph G, and um, so path is basically just a um, yeah sequence of um, edges that you can traverse such that each of these is an edge. Okay. So what is Hamiltonian? It says that every is there a path which um, which takes or which is yeah, okay. Okay, so you want this path to be incident to take every vertex that's in the graph. Okay, but you can't repeat a vertex again. So for example, you if you say 2 3 um okay, if you say 3 2 1 2 4 5, okay, that means you go like this: 3 to 2, 2 to 1, from 1 you go back to 2, go to 4, and then go to 5. So in this path, every vertex has occurred once. Okay, so each of this vertex appears in this path, but there is a vertex which appears twice, so this is not a Hamiltonian path. So it should contain every vertex exactly once. So do you see a Hamiltonian path in this graph?
1 to 2, 3 to 4, 4 to 5.
Exactly, yeah. So this is a valid Hamiltonian path because it um, takes each vertex exactly once. Yeah. So what will be your certificate for this problem? So you want to say yes if G contains a Hamiltonian path and no otherwise.
What was the question? Could not hear.
Yeah. So how do you show that Hamiltonian path is in NP?
Okay, so in a certificate would be a sequence of the vertices, and if I can check that every vertex has been covered in that sequence, then yeah, that is a Hamiltonian path.
Yeah, and
We're doing path or circuitry? Path.
path.
Oh, all right, yeah.
Yeah, and also check if every adjacent pair of vertices are, every consecutive pair of vertices actually have an edge in the graph. Okay. Okay, so yeah, this is also done. Maybe this one you can check later on, but let's try this. Okay, so so the input to you is a Boolean formula. What is a Boolean formula? Um you are given um, you have some variables x1 to xn, and they can take 0 1 values. Okay, each xi can take 0 1 values. Okay, and what is a Boolean formula? Boolean formula is yeah, so it's just uh, some combination of these variables by either doing a conjunction, or sorry, by either doing a disjunction or conjunction or negations. Okay, so some combination of these, or let's say I can have x6 bar and x1. So these are the three operations you are allowed. You're allowed
Ma'am,
to.
conjunction means or operation.
Conjunction means and operation, disjunction means or operation. So this is,
Conjunction means or, no and.
yeah, and this is, okay. So this is what we call a formula, generally denoted by phi. Okay, and let's say, for example, I'm going to give you some substitution. Okay, let's say consider the following assignment. Let's say x1 is 0. Okay, let's suppose x4 is 1 and everything else is 0. x1, x2, x3, sorry, x5, x6, all of them are 0. Okay, so this is a particular boolean assignment. Each of them take value 0 to 1. So let's say, suppose consider this particular assignment. Then what is the value of this? What does this formula evaluate to? Just put ones and zeros here and evaluate that. So what would that be? x1 is 0, 0 or 1. Okay, I should put some, and 0, and okay, I should also, x4 is 1 or 0 or 1 and 0. Okay, so I'm just substituting the values into the respective places. So what is this? 0 or 1 is a 1, so you get 1 and 0, and 1 or 0 is 1, so you get a 1. 1 and 0 is a 0, so you get a 0. So what is this further? Simplifying this, 1 and 0 is 0, so you have 0 and 1 or 0. Again, this is 0, this is 0, so this will turn out to be 0. Okay, so the question is, okay, if I give you this particular assignment and I evaluate it on this function, then the formula evaluates to 0. This is what happened, and you say that the formula evaluates to 0. But the question is it possible that I can come up with some other assignment? Maybe I'll take x1, x2, x3 to be 1, everything else to be 0, then, or some other combination. Can I come up with some assignment of variables such that this formula evaluates to 1? Okay, so that is the satisfiability question. So this is the satisfiability problem, which is given phi, a formula phi, you are going to say yes if there is an assignment okay, there is some assignment A to variables x1 to xn such that, and let's say that assignment is a1, a2 and so on up to an, where a1 to an are some boolean values. Okay, such that phi of a1 to an is equal to 1. Sorry. In other words, phi is satisfiable. And then you say no otherwise. Okay.
Ma'am, when phi is satisfiable?
Yeah, if there is, so if there is some other assignment I can come up with, that maybe I'll say x1, x2, x3 is 1 and everything else is 0, then I evaluate on those values. If that value turns out to be 1, then you say that phi is satisfiable. In this case, for this assignment it came to 0, but if I substitute into something else, maybe I'll get a 1. So can you see a satisfiable assignment here? What should I put the values of x size, x1 to x6, so that this thing will evaluate to 1?
Okay, ma'am.
Okay, so one example for making this evaluate to 1 is put x1 as 1, put x6 as 0. For everything else it doesn't matter what you put. Okay, let's say I put everything else as 0. Then look at what happens to this. What is x6 bar and x1? This will be 1 and 1, which is 1. Okay, and then you have this other part here, this big part. no matter what this is, whether this is 0 or 1, it doesn't matter because you're taking an OR with a 1. This evaluates to 1, then the entire formula will evaluate to 1. So therefore for this particular assignment, phi of this particular assignment, or let's say x1 is equal to 1, x2 is equal to 0, and so on, x6 is equal to 0, this formula will evaluate to 1. So this is a satisfiable formula. Okay.
Yes, ma'am.
Okay. So this is the problem that's given to you. Given a phi, check if there is an assignment such that the formula evaluates to 1. Oh, so this is equal to, yeah. So is this problem in NP? If it is in NP, then do you see a small certificate and an efficient verification?
So there would be an assignment of the Boolean literals, say Boolean literals ranging from x1 till xn, and the length of the certificate would be n. And if that makes the Boolean expression satisfiable, then yeah, and this satisfiability can be checked in the polynomial effort.
Yeah.
So this is an NP.
Yeah. So maybe I'll not write that, but yeah, try to, yeah, everyone try to write this step by step like we did earlier. Okay. So this is also in NP. Okay, I think there's only one more question that I'll leave for now. Okay. So maybe I think I'll cut down today's session a little bit earlier. So are there any questions about whatever we discussed so far?
So it's related to the verification, the polynomial time verification, and the verifier should take polynomial time in terms of the size of the certificate,
The length of the input.
length of the
Yeah, you
input.
can say the same thing. Yeah, it's the same thing because the length of the certificate itself is polynomial sized in terms of input.
So, I mean, like say the verifier is taking an effort of the order of n, and we are representing the certificate in binary. So then, in terms of the size of the certificate, the verifier is taking exponential time.
No, so
Like in the case of the composite, say we represented number n into the binary, and now say if the verifier takes an effort of the order of n, say assume that
yeah,
to
just
check, yeah.
yeah, just give me a minute, okay? The pencil is charging. I'll write down whatever you're saying. Okay. Hmm. Okay, yeah. So the input size is
So input is represented in binary,
hmm.
and so
So
the size of the input is log n, and the verifier is taking an effort of the order of n. So now, I mean, input would mean that the certificate, the length of the certificate is also log n. Length of the certificate is also log n.
log into the C. You're
Yes.
allowing, yeah.
Yes. And the verifier is taking of the order of the order of n. So now this verifier is taking exponential time compared to the
Length of the
size of
input.
the
Yeah.
certificate. Okay, all right,
Hmm.
all right. So yeah, and what if I represent the certificate in unary? Then this is taking the polynomial time. Is this?
Yeah, but um, I mean, if you represent it in unary, you would, yeah. I mean, you would be exponential in terms of length of x, right?
Length of input.
Hmm. Yeah.
Oh, I see. Okay, okay. So what if I give the length? What if the input and certificate everything is in unary?
Yeah.
So in that case, it's fine that the verifier is taking polynomial time.
So
So
if length of
basically, my question is that how, I mean, just on the basis of the representation of, just by changing the representation strategy of the input or the certificate, all of a sudden the problem changes from the
the yeah.
initial of the problem changes. So how does this happen?
Um, well, um, if you are giving, if you represent the input in a larger space, that means you are giving the algorithm more time.
Yes.
Hmm. So, yeah, so it falls into a smaller class. Whereas if you give it lesser input in lesser size in the first place, then it has less amount of time. So, yeah, so then that class can only be higher. I mean, cannot be below this. So, I mean, so for a lot of problems, therefore, it matters how you represent the input, because if you look at a graph and you give it as an adjacency matrix, you are taking n square, n cross n matrix. Let's say the size of input is n square. So, maybe there is an algorithm to solve the problem which takes n to the c amount of time. But now, if I give you, let's say, the matrix is not very you had an n cross n matrix, and these are the adjacencies, okay? But let's say I know for a fact that my input is only going to have some log n number of ones, okay? Only there are very few ones. So then I don't need to give you this entire matrix and take n square amount of time. What I would rather do is, I'll tell you where there are ones. I'll tell you at this, sorry,
Yes.
yeah.
And in the definition you gave how much time is allowed for the verifier. Verifier should run in the polynomial.
Yeah, length of certificate should be length of x to the c, and this should also run in length of x to the some c prime
Okay. Polynomial of the length of the input.
input. Yeah, but if this is polynomial in length of input, then polynomial of this will also be some polynomial, right? Because if you do length of x to the c to the sum d, this is still length of x to the some other constant which is cd. So that is still polynomial.
Yes, yes. I understood this. Thanks.
Ma'am, you generate a certifications and verifier based on a Boolean expression, but could we also perform a verifier or certification based on tuning machine, CFL, and the finite automata, regular language? Can I do that?
Uh, so input is a machine, let's say a
Yeah,
Turing
yeah.
machine, and what do you want to check? Um,
Verifier and certificate. How can we
yeah, so verifier and
get a
certificate,
output? And that can you example given same kind of.
where the object is Turing machine, or some machine that of your choice. Okay, so okay, let just let the pencil charge. Okay, so let us take an example where input to you is a DFA m, and you are given a string, some binary string. You want to say yes if m accepts w, no otherwise. Okay, is this question okay? And then you are asking whether there is a certificate and a verifier for this. Is that um
Yes, ma'am. It is also done, I think,
hmm.
the first time. But can you CFL?
Yeah, I mean you can replace the DFA and Turing machine, and if you replace this with, I mean, if you replace this with, for example, a Turing machine, okay, then this question itself does not arise, because this problem is nothing but membership or ATM problem, which is given m comma w, check if m accepts w, and you know for a fact that this is an undecidable problem. ATM is undecidable. Okay, so if it is not decidable at all, then it's, we are not even sure that it will halt. So forget about the verification and time complexity and everything. It's not decidable in the first place. So yeah, so that problem is out here. Okay, and we are looking at this class, and we okay, there is NP here, but yeah, we are looking at this class, and the problem is out there. Okay, so we can't talk about certificates and verifiers for um, these kind of problems.
Okay, ma'am. Fine.
Okay, but yeah, but you can have this sort of thing given input m in the form of a binary encoding. um, Check if m has um, let's say odd number of states. Okay, not really this, but mm, okay, what could be some simple property? mm, mm, 20 states or something. Okay, I'm just taking something very trivial. Yeah, so yeah, so to talk about NPP and all these problems, we first need to be within the decidables um, set. Yeah, and yeah, so for example, these kinds of things are something you can easily check, so you can talk about verifiers and certificates here. Okay. Okay, any other questions?
From my side, no question arises in my mind. So I think what.
Yeah, sure. Okay, so next we will meet on yeah, Monday, just 30th March, same time, 7 p.m. to 9 p.m. Okay.
Thank you so very much. Thanks again. Bye.
Yeah,
Good
thank you. Yeah, bye.